What's the difference between the universe and the German Autobahn? The universe has a speed limit, okay? Logically flawed dad jokes aside, the fact that the speed of light, known simply as c in scientific notation, is the unbreakable speed limit of the universe is one of the fundamental laws that underpins our understanding of physics. If you are fascinated by the fundamental laws governing our universe, hit that subscribe button. We're a new channel called Past the Surface and trying to reach our first 1,000 subscribers. So joining now makes you one of our true pioneers. But why exactly is this the case, and can we really not go any faster? Before we get into all of that, let's start with the basics. Just how fast is light? This is normally the part of the video where I proclaim that this is a question scientists have puzzled over for millennia, but when it comes to the speed of light, that actually isn't the case. Because for much of human history, it was thought that light didn't have speed at all, that it simply moved instantaneously, reaching its destination at the precise moment it left its point of origin. From our smug vantage point here in the 21st century, that might seem pretty stupid. How could anything, even something as clearly nippy as light, move at what would amount to infinite speed? But when you actually think about it, it isn't all that crazy a conclusion to come to. After all, how the hell do you even begin to go about demonstrating that light has a finite speed? If you wanted to prove that sound doesn't travel at an infinite speed, all you'd have to do is grab a friend, get him to stand as far away from you as possible, and ask him to vigorously bang a drum. Then buy him that pint you promised so he doesn't stop associating with you. The delay between what your eyes see and what your ears hear would show you immediately that sound has a finite speed. And, to be honest, you don't even need to set up a crude experiment like this to prove this rather obvious fact. We see the finite speed of sound in action all the time in everyday life. The boom that comes several seconds after a firework lights up the sky, for example, or an echo in a large empty room. Even the cool ripple effect you get at concerts with the crowd bouncing in time to the music as sound waves travel towards the back of the auditorium. Try and carry out a similar experiment with light. However, something the great Italian polymath Galileo Galilei attempted in 1638, and it's an altogether different story. The experiment Galileo set up was simple. He and one of his assistants each took a covered lantern to the top of two distant hills. Galileo was to uncover his lantern first, and as soon as his assistant saw the light, he would uncover his own lantern, sending the signal back to Galileo. Using his pulse, or perhaps a water clock, Galileo would be able to time how long it took for light to travel between the two hilltops, with a small delay introduced by the reaction time of his assistant. The problem was, this small delay was in fact far, far larger than the actual time it took for the light from the lanterns to cover the distance between the hilltops, which would have been a matter of microseconds. The experiment was a failure, leaving Galileo to conclude that either light did indeed travel instantaneously, or that it moved at a truly incredible speed, considering the fact that Galileo is quite rightly considered one of the greatest geniuses in history. It's quite surprising that we had to wait less than 40 years from the date of this failed experiment for someone else to come along and demonstrate for the first time that light does indeed have a finite speed. That man was Danish astronomer Ole Roma, although ironically enough, his breakthrough was based on an unrelated piece of Galileo's own work. In 1598, King Philip III of Spain offered a prize to anyone who could figure out a way of measuring the longitude of a ship at sea that was out of sight of land. And in 1616, Galileo did exactly that. He had recently discovered the existence of one of Jupiter's moons, Io, and his solution to the king's challenge rested on using the cyclical timing of the eclipses of Jupiter by Io as a kind of cosmic clock. Exactly how that worked isn't relevant for our purposes. But what is relevant is something strange. Ole Roma and fellow astronomer Jean Piccard, not that one, noticed about the period between these eclipses, which seemed to vary depending on the time of the year. Roma realized the anomaly could be explained by the different distances the light was traveling as the Earth and Jupiter moved further, apart or closer together in their respective orbits around the Sun. And if distance was having an impact on the time it took for the light to arrive here on Earth, then it must have been traveling at a finite speed. Roma even had a go at estimating what that speed might be based on his observations. His answer was within a creditable 25% of the real figure. Over the years since, scores of scientists have had a crack at calculating a more accurate measurement for C. By the 20th century, thanks to fancy techniques with exotic names like cavity resonance and laser interferometry, we were able to calculate an exact figure for the speed of light in a vacuum, which is precisely 670,616,629 miles per hour. It's a smidge over 1 billion kilometers an hour, or for you visual learners out there, fast enough for light to travel 7.5 times around the equator in a single second. Yeah, no wonder Galileo struggled to pin it down using his pulse and a couple of lanterns. As a random aside, we now use the speed of light as the basis for how we measure distance too. As of 1983, the official definition of a meter is the distance traveled by light in a vacuum in 1, 299,792,458 of a second, give or take. But does the speed of light really represent the upper limit for the universe? Or is it possible to make something travel faster? Well, there are two ways of approaching that question. The first is practical, and the second, theoretical. Let's start with the practical one. Could we, with our present technology, make something travel faster than the speed of light? Well, the fastest speed ever achieved by a man-made object is a record owned by the Parker Solar Probe, which was landed by NASA in 2018 to investigate the sun's outer corona. That's the aura of plasma that surrounds our home star, and it's this you can see as a glowing halo during a solar eclipse. The Parker Solar Probe is already rattling on at a fair old clip, but by the year 2025, it will have reached its maximum speed, 430,000 miles per hour. That's pretty damn fast. For context, a high-velocity bullet fired from a modern rifle might reach a maximum speed of around 2,500 miles per hour, which is only about 0.6% of the speed that the Parker Solar Probe will top out at. If Superman had a baby with Sonic the Hedgehog, it wouldn't come close to the speed of the Parker Solar Probe. Yet the probe, the bullet, or the mutant superhero offspring for that matter, still ain't got nothing on light. The Parker Solar Probe, if you're wondering, would be traveling at around 0.006% of the speed of light. Or to put it another way, if light was Usain Bolt, the Parker Solar Probe would be an asthmatic geriatric with one leg, whose single foot had been superglued to the floor whilst he wasn't looking. So no, from a practical standpoint, faster than light travel is pretty much out of the question for our species with present technology. Anyway, although having said that, we have managed to accelerate non-man-made objects, things we basically just found lying around the universe, to speeds that are much faster than the Parker Solar Probe. The Large Hadron Collider at CERN, buried beneath the border between Switzerland and France near Geneva, is the world's most powerful particle accelerator. It's used to explore conditions as they were in the universe directly after the Big Bang, investigates the general weirdness that is dark matter and dark energy, and it was essential to proving the existence of the fabled Higgs boson, known commonly as the God particle. Using the facility's 27-kilometer particle accelerator, the largest in the world, we've managed to get charged particles like electrons to within a tiny fraction of a percent of the speed of light. But no matter how hard we try, we've never quite been able to get them all the way there, and we never will. Because here's where we come to the theoretical part of the answer to our question. And unfortunately, it leaves very little wiggle room for FTL travel. As an object moves faster, it appears to gain mass. This isn't something we're aware of on a day-to-day basis, because the effect only really kicks in when we get very close to the speed of light. But we have to be able to measure it experimentally in particle accelerators like the Large Hadron Collider. The closer we get to the speed of light, the more an object's mass increases, and the more energy is required to accelerate that object any further. Before it actually reaches the speed of light, both its mass and therefore the energy required to accelerate it further appear to become infinite. Put simply, the laws of physics are pretty clear on the impossibility of superluminal travel. Thanks, Einstein. But wait a second. If light speed travel is impossible, how come light can do it? That's because light is made up of photons. And like a supermodel after 2 months of cucumber juice and paying a charlatan in a lab coat to suck her bowels for a plastic tube, photons have no mass, meaning they're exempt from the above relationship between mass and energy. In fact, photons can only travel at the speed of light, never faster and never slower. You may have heard that light slows down when it passes through a medium like water or glass, and that's true, but the photons themselves never slow down. They don't experience acceleration or deceleration either. The moment they are brought into existence, they are traveling at the speed of light. So I guess that about wraps things up for this video, or does it? Because, hang on a second, couldn't I myself push light over this apparently unbreakable speed limit of our universe just by going for a light jog? Now, as you can probably imagine, I'm a pretty nifty mover, with a top speed clocked at a solid 19 miles per hour. 20 if I have trimmed my mustache. Drag coefficient can be a bitch. If I were to run at said top speed whilst holding a shining torch out in front of me, the light from that torch would be traveling a smidge over the speed of light, at precisely c plus 20 miles per hour, thus breaking the unbreakable speed limit of our universe, right? Actually, wrong. Whilst the logic seems to check out, except maybe for the part about my top speed, I'm not as young as I used to be. It turns out that not even light can break the universe's speed limit. It must always travel at the speed of light regardless of who observes it and from where, which is, when you think about it, really bloody weird. According to classical relativity, velocity is a relative concept. If you're standing on the platform, a passing train might appear to be traveling at 100 miles per hour relative to you. But to a passenger on the train, providing they don't happen to be looking out of the window, the train would appear to be stationary. It's all a matter of perspective. If you'd like a more immediate example, take a look at the ground beneath your feet. I'm assuming it's nice and stationary right now, assuming you haven't been sampling any of those funny colored pills again lately. But then again, we know that the Earth is actually rotating at around 1,000 miles per hour at the equator, not to mention orbiting the Sun at a healthy 67,000 miles per hour. So if you change your frame of reference, the ground beneath your feet is actually moving very, very fast indeed. An object's speed all depends on the relative speed of the observer, but light doesn't work that way. You could, in fact, attach a torch to the front of a rocket traveling at 99% of the speed of light, and the light from that torch would still be traveling at precisely the speed of light, no matter where you are observing it from. So how can this be possible? Like many of science's most annoying problems, it was Einstein who got to the bottom of this apparent paradox. His stroke of genius was to realize that if the speed of light wasn't changing, even as the relative velocities of the objects around it were, something else must be changing: time. Put simply, the faster an object moves through space, not only does it appear to gain mass, it also moves more slowly through time. Einstein had come to the startling realization that time was not constant, as had always been believed, and the foundation for his theory of special relativity was laid. The logical inference of this discovery is that light is a constant. That's why it gets to join a special club with a very limited membership, the Universal Constant Club, sometimes called physical constants. These are measurable components of the universe that never change, such as gravity. The idea that time slows down for objects traveling at speed is, for once of a better phrase, trippy as all hell. But this relativistic effect, known as time dilation, can actually be measured in the real world. So it isn't just some theoretical weirdness that's confined to the pages of our physics textbooks. In October 1971, physicists Joseph Haffel and Richard Keating conducted an experiment where 4 incredibly accurate cesium beam atomic clocks were flown twice around the world aboard commercial airplanes. When they compared the clocks with others that had spent the duration of the experiment chilling on terra firma, they found that the times displayed were different. Time on the airplanes had passed more slowly than it had on the ground. Not only that, the amount by which time had slowed exactly mirrored Einstein's predictions. But before you go booking yourself on a never-ending flight around the world tour in the hopes of outliving all of us suckers down here on Earth, at the kind of speeds we're talking about here, the slowing of time is measured in nanoseconds. Still, our global GPS system, which relies on satellites whizzing around in orbit at high speed to triangulate positions here on Earth, has to account for time dilation, or else that handy map in your mobile phone would cease to be usable at all. Okay, enough of the mind and time-bending stuff. The key takeaway from this video is that FTL travel isn't possible because, well, Einstein says so. Alright, although now, don't get all excited or anything, but there may just be a way of kinder achieving FTL travel without actually accidentally breaking any fundamental laws of the universe in the process. A loophole, if you will. Although confusingly, this loophole was actually a wormhole. Einstein, he really got around, didn't he? He predicted the existence of wormholes in his general theory of relativity. We haven't actually found any yet, but if they do exist, wormholes might essentially represent shortcuts through space caused by the warping of space-time. And by traveling through one, you could potentially cover billions of light years in mere seconds without having to move faster than light at any point, which would prove very valuable if we ever have ambitions of exploring other stars and even other galaxies. Okay, this one goes a bit weird. So to sum up, light is fast, but you can't make anything else travel that fast because Einstein... Oh, and if you start thinking too much about special relativity, the universe as you know it will stop making any kind of sense, and bits of your brain will probably start dribbling out of your nose. And on that note, thanks for watching.